Okay guys, welcome back to our channel. In today's class, I want to take us through quantum numbers, the types of quantum numbers, and the various type of questions that could be asked under quantum numbers. Now, first and foremost, we have four major types of quantum numbers. We have the principal quantum number that is designated with a symbol of n. We have azimuthal quantum number, which is also known as subsidiary, which has a symbol of L. We have magnetic quantum number, which has a symbol of Ml, and of course we have the spin quantum numbers. Okay, so we're going to take them one after the other. Alright, so for the first one, we'll say for principal quantum number. Principal quantum number. Now, principal quantum number describes the shell or the energy level of an atom. I say it describes the shell or the energy level of an atom. Now, the value of n, the value of principal quantum number usually starts from 1. Right? N can start from 1. N can be 1, it can be 2, it can be 3, it can be 4. Till all positive integers, till infinity, all positive integers. Now let me take our minds back. People will recall, every atom has what we call shell. Shell is same as energy level. Alright, so the nucleus is an atom, this is a nucleus of an atom. So I have the first shell, I have the second shell here, and I have the third shell. So the basic work of this principle describes this shell. Now we know that the first shell is K, the second one is L, and the third one is N. Now, according to principal quantum number, the first shell is N equals to 1, the second shell is N equals to 2, and the third shell is N equals to 3. Alright, so that is that for principal quantum numbers. It describes the shell or the energy level of an atom. Okay, now note that N can never have a value of 0. Alright, now let's look at the second type of quantum number. The second type of quantum number is the azimuthal or the subsidiary. To say the second one is azimuthal or the subsidiary. Now this has the symbol of L. Now what is the function? What is the work of this azimuthal? I'll list it out. It describes the shape of an orbital, that's the first function of this. S orbital is known to have spherical shape, B is dumbbell, D is double dumbbell. Now we actually were able to know this as because of the azimuthal or the subsidiary quantum number. Now the next function or the use of this is that it tells us the types of subshell present in a shell. Okay, and the last one I would also say it tells us the type of orbital. It tells the types of orbitals that are present in an atom or in a shell. Alright, now L azimuthal depends on principal. Let's use this. Azimuthal quantum number depends on the principal. Why do I say so? Because the value of L varies or ranges from 0 to n minus 1. It ranges from 0, start from 0 and stop at n minus 1. Let me show you what I mean here. What exactly is what I mean? What I mean is that if you know the value of n, you can get the value of L. Remember we said the formula for L is that it starts from 0 and stops at n minus 1. That means that if n is equal to 2, okay, the n is equals to 2, so the value for L, it will start from 0 and will stop at n minus 1. What is n here? 2. 2 minus 1 is 1. So the value for total is going to be 0 and 1. Now what if n is equals to 3? If n is equals to 3, L will start from 0 and ends at n minus 1. What is our n here? 2. 3 minus 1 is 2. Between 0 and 2, which whole number comes between 0 and 2? 1. Remember they said, start from 0. They did not say 0 and n minus 1. So it starts from 0 and stop at n minus 1. That means in between this and this, there should be a whole number in the middle. So for n equals to 3, L will start from 0 and stop at n minus 1. What is our n here? 3 minus 1 is 2. So between 0 and 2 we have 1. Now, if n is equals to 4, L becomes 0. It will stop at n minus 1. What is n here? 4. 4 minus 1 is 3. This is 1 and 2. Alright, I believe this is actually clear enough. Okay. Now what if n is equals to 5? If n is equals to 5, L will start from 0 and ends at n minus 1. N minus 1, in this case, n is 5. 5 minus 1 is 4. So between 0 and 4, what are the whole numbers here? You have 1, 2, 3. So if n is equals to 5, L will have the value of 0, 1, 2, 3, and 4. And mind you that L depends on n. Without n, we cannot find L. Okay, how to get the value of L when n is given. Now, but then, as metal quantum number give a letter designation for its numbers, right? That simply means if n equals to 0, there's meant to be a letter to designate 0. That letter is also called orbital. So I'm going to be walking us through on how to know the different letters. So we have the azimuthal quantum number. We have azimuthal quantum number, which is L. We have the designation, which is also known as the orbital. Okay, so if this is L equals to 0, this is 1, this is 2, and this is 3. So if L equals to 0, the letter here is S. If L equals to 1, the letter here is going to be B. If L equals to 2, the letter here is D. And if L equals to 3, the letter here is F. That simply means that, what does L equals to 0 stand for? That means any orbital that contains, that has 0 as L, it means that that is S orbital. So let me give you an example. We say, example, if n equals to 2, the value for our L is going to be equals to 0 and 1. I just showed us here. Alright, now, this 0 here means that the designation for 0 in terms of azimuthal, this is S. The designation for 1 is B. Now, if I combine this S with these 2, I think this simply means that for shell number 2 can have 2 subshell, 2S and 2B. We call these 2S and 2B subshell of shell number what? Number 2. Okay. If n equals to 3, recall that our L will be 0, 1, and 2 based on what we did here previously. Now the value for L equals to 0, the letter designation for L equals to 0 is S. The letter designation for L equals to 1 is B, and this is D. So if you combine this S with this 3, this will give us what we call the subshell. So this is 3S, 3B, and 3D. So you can see that for shell number 2, we have 2 subshells. For shell number 3, we have 3 subshells. That is why you will never see 2 having 2D. Right? 2 can only take 2S and 2B. How about 1? If n equals to 1, that is for the first shell. Our L is always equals to 0, compulsorily. Because remember we said that L depends on n, so if n equals to 1, L is going to be 0. We're going to start from 0 and to end at n minus 1. n in this case is 1. 1 minus 1 is 0, so you just write 0. Alright, it's nothing like you don't write 0 twice. So this is 0. What is the designation that represents this guy? S. If you combine this with this, you have 1s. So for the first shell, it has 1s. For the second shell, we have two subshells, 2s and 2p. For the third shell, we have 3s, 3p, and 3d. Now with this we've actually done with the introductory part of azimuthal. Now let's look at magnetic quantum number. Which has a symbol of ml. Now basically, this particular quantum number, right, it describes the orientation in space of the orbitals. I said it describes the orientation in space of the orbitals. It describes the orientation in space of orbital. The next guy is that it divides orbitals into suborbital. I know you must have heard of p orbital has three suborbitals, the px, the py, and the pz. Alright, now how did we actually come to that is because of the help of magnetic. Okay, so let's see how magnetic varies. Now before then, magnetic quantum number, so let's come back to this side. Let's move back to this side. Magnetic quantum number depends on azimuthal. Depends on azimuthal. If you actually notice, depends on azimuthal. Now magnetic quantum number varies from minus L to 0 to plus L. Now if you notice, when we were talking about azimuthal quantum number, we said that azimuthal depends on principal. Right? That means if you know the value of principal, obviously you'll be able to know the value of azimuthal. Now we are actually talking about magnetic quantum numbers. Now we are saying that magnetic depends on azimuthal. That simply means azimuthal has a letter designation of L, right? While magnetic has a letter designation of ML. So it means that for every value for azimuthal, we should have the value for ML. Right? Now let's see this. Let's look at how it works. I'll say if L equals to 1, remember, L equals to 1, which orbital has L equals to 1? That is p orbital. The table I cleaned up earlier showed that L equals to 0 is for S orbital, L equals to 1 is for P. So this is p orbital. Okay, now p orbital is subdivided into 3. Now let's look at this. NL for this would be, remember we said we're going to start from the negative of the L to the 0 and to the positive. N equals to 1, alright? This becomes minus 1, 0, and plus 1. Now these are the values for the NL. Alright, so we're going to, each of these values stand for an orbital. So I'll come here. This gives rise to 3 boxes. The ML, the minus 1 is the PX, the 0 is a PY, and the plus 1 is a PZ. Right? So these values are constant. So ML equals to minus 1 is PX, ML equals to 0 is PY, ML equals to plus 1 is PZ. Let me take it one more time. How do we get minus 1, 0, and plus 1? Because if N equals to 1, we take the negative, we start from the negative of 1. After minus 1 is 0. We will take in whole numbers. N equals to 1, we will take minus 1, 0, and plus 1. What if N equals to 0? If L equals to 0, that's S orbital. Our NL must be 0 because we don't have anything like, there's nothing like minus 0, 0, and plus 0. You understand? So once N equals to 0, NL must be 0 is a must. If n equals to 1, remember the table I gave us earlier that I earlier explained that each value for the orbital has a vector designation, which is also known as the orbital. So for n equals to 0, that's s orbital, the magnetic value is equals to 0. If n equals to 1, now our NL for this would be minus 1, 0, and plus 1. Okay, now how did we come about this? Remember, this varies stand for negative of the L, so the LK is 1, so stand for minus 1, 0, and plus 1. Remember, each of these values stands for orbital. Alright, so that is how P has 3 suborbitals. So we have the minus 1 has Ex, the 0 has Ey, and this has Ez. Right? Just in case you're wondering how we got that. Now, if L equals to 2, that is d orbital. If L equals to 2, that is d orbital. Now, the external for this would be, it's not going to be minus 2, 0, and plus 2. Right? It's not going to be this. Now, this arrows is actually pointing. That means you move from this towards 0. Whatever you have in the middle that is an integer, you record it. So it's not going to be minus 2, 0, and plus because here is 2. But instead, it's going to be minus 2. After minus 1, which other whole number do we have? Minus 1. After minus 1, after 1, which other whole number? None. We come down to 0. Okay. So this becomes minus 2, minus 1, 0, plus 1, plus 2. Okay. Now, how do we actually designate this? Alright, this is the xy. This is the xz. This is the yz. This is the x squared, y squared, and this is the z squared. Now, these values are all constant. They are constant. Now, the orbital has 5 suborbitals. D has 5 suborbitals. The xy, the first one, the xz, the second one, the yz, the third, this, and these are 5. Now, you may want to ask, how did this come about? Of course, that is higher than the scope of this course. So you just need to know that for n equals to 2, NL is minus 2, minus 1, 0, plus 1, and plus 2. Now, the designation for n equals to minus 2 here is the xy for the orbital. Now, for the orbital, m equals to minus 1 is the x, m equals to 0 is the y, m equals to plus 1 is the z. And it's important to know that P has 3 suborbitals. Px, Py, and Pz. And x orbital has no suborbitals. It's just x. Okay. So with that now, we're rapidly done with the explanation of the azimuthal quantum number, magnetic quantum number. So let's start the last one before we start solving problems. Okay, guys. The last quantum number we'd like to explain before we proceed to solving of questions is the spin quantum number, which is number 4. Spin quantum number, which has the symbol of ms or s. Alright. Now, what is the purpose of spin? Now, spin describes the orientation of the spin of an electron. Describes the orientation of the spin of an electron. Now, in every orbital, If you don't want to put the range, you can see it describes the spin of an electron. In every orbital, each of these balls can take maximum of 2 electrons, each of these small balls. The first one must spin up and the next one must spin down. Right? Now, spin quantum number describes their spin. The one that is spinning up is plus half. The one that is spinning down is minus half. It therefore means that for spin quantum numbers, right, spin can only have 2 values for electrons, plus half for upward spin plus half and then we have minus half. Downward spin. Okay? So just in case you're being asked, the one that spins up is a positive half, the one that spins down is a negative half. So with this now, we've actually come to the end of this explanation. The next thing we're going to be doing now is to solve problems that cuts across each of them. Right? So I'll be listing out the various ways question can be asked as far as quantum number is concerned. There are lots of them, right? But I'm just going to pick out the one that is mostly very important for those persons writing, those persons in A1 and also those persons writing JAM. Okay guys, we want to look at the various ways question can be asked under quantum numbers. There are so many of them, but we just want to look at the summary of all of them. And the first one is writing possible values for L and ML. L is azimuthal, ML is magnetic when N is given. Recall that N is actually principal quantum number, L is azimuthal, and ML is the magnetic. So that's the first question. The second one is giving values for quantum numbers when subshell designations are given. The next one is writing designation when quantum numbers are. So it means like this number 2 and number 3, they are more like opposite of each other. Number 4 says calculation of maximum number of electrons. Right? Okay? When quantum numbers are given. When quantum numbers are given. Okay, of course, we're going to see that shortly. Quantum numbers are given. Now, number 5 is correcting wrong set of quantum numbers. So, they can give you a wrong set of quantum numbers and you'll be asked to correct it. Okay, so how are you going to go about it? And that is everything we want to look at here. Now, let's look at the first one. The first one, writing possible value for L and ML when N is given. Okay, so let's look at the first question. Let's look at the questions and see how we're going to solve them. For example, they say, give the possible values. Give the possible values of L and ML when N is equals to 3. That's the question. Recall that L, which is azimuthal, depends on N, which is a principal. So it means that once you know the value of N, obviously you can know the value of L. And once you know the value of L, you can know the value of ML because ML depends on L. So this becomes, we have solution. If N is equals to 3, the value for L becomes 0, 1, and 2. You may want to ask how. Now remember that N is azimuthal, N is always starting from 0 and ending at N minus 1. Now, so in this case now you put 0 here, N minus 1. What is N in this case? 3. 3 minus 1 is 2. In between 0 and 2, what is the whole number that comes in there? We have 1. So this becomes 0, 1, 2. Alright. Now recall that ML depends on L. For every value of L, there is ML. The color told us that once n equals to 0, ml must be equals to 0. Is a must. It's a must because ml is always having minus L to 0 to plus L. So there's nothing like minus 0, 0 and plus 0. So 0 is 0. Okay? So this becomes so for n equals to 0, ml equals to 0. For n equals to 1, ml becomes minus 1, 0 and plus 1. You ask for the possible, all the values that are possible. Right? Now for n equals to 2, ml is going to be minus 2, minus 1, 0, plus 1 and plus 2. And there you go. That is the answer to that question. Alright? Alright, so let's look at the next question. Please, if you have any question, make sure you drop it on the comment section. I'll be here to answer your questions live and direct. Alright, so let's start the next question. Question number 2. Giving values for quantum numbers. When soft-shell designation is given. Giving value for quantum numbers when soft-shell designation is given. Okay, now let's look at this. What does particular question mean? Let's look at an example. Alright? We have an example. What is the value of N, L, and ML for the following: A, 2s, B, 2p, C, 2px. Okay, guys. We have the next question under the number 2 is giving value for quantum numbers when soft-shell designations are given. So we have a question here. It said, what is the value of N, L, and ML for the following soft shells? Now recall that our N here is actually the principal quantum number, our L is actually the azimuthal, and our ML is the magnetic. Alright? So, for the first question, let's look at the A part. For the A, they say 2x. Class, this number, these whole numbers you see here, they are the shells. These numbers are the shells, and shells are said as energy level. And which quantum number describes the shell is principal. So therefore, this N here, this is N, that is second energy level, that is the second shell. This S, recall when we were talking about azimuthal, we said azimuthal used a letter designation, which we called an orbital to designate quantum numbers. Now, so this is going to be our L. And remember that once you know the value of L, you know your ML, right? So let's get this straight. For this particular question here, our N is this energy level. These numbers in front of this are the N, that is the principal quantum number. So our N is equals to 2. Our L, remember this S, right, is actually a designation when N is equals to 0. So anytime N equals to 0, that 0 can be replaced with S. So our L is equals to 0. And recall that anytime N equals to 0, ML must be 0. So the value of N, L, and ML when N equals to 2s, when we have 2s, n equals to 2, n equals to 0, and nl equals to 0. Okay. So that is that for this particular question. Now let's look at the next one. B, we have 2p. Once again, our n is going to be 2. Now, n here, principal quantum number is 2 because this is a shell. This p is azimuthal quantum number that was represented with a letter or an orbital. And if you could recall, for p, if you could recall, we have something like this, azimuthal, and we have orbital. If this n equals to 0, this is x. If n equals to 1, this is p. If n equals to 2, this is d. And this is n. So that means if I see a letter x stands for n equals to 0. If I see a letter p stands for n equals to 1. Letter d stands for n equals to 2. Letter f stands for l equals to 3. And from the question they say we should give the value of n, l, and ml. So here, our L, the letter here is P, and letter P has L equals to 1, so here is 1. And recall that once L is known, you can get your ML. ML will always start from -1, 0 to +1. So in this case now, my ML becomes -1, 0, and +1. That is my ML for this particular question. Alright, so let's look at option C. If you have any question, once again, your comment section is there for you. Drop it, of course, I'll answer the question right away. Now let's look at option C. Option C is 2px. Now if you notice, the two previous questions we solved did not have a subscript attached to them, but this particular one has a subscript. So how are we going to solve this? Don't go anywhere, I'm here with you guys. Our n here is equals to 2. Our L, recall that for P, once you see P, the L value for P is always equals to 1. Now remember, in the previous case, when it was just P, we said NL equals to -1, 0, and +1. Right? But the moment they put here to be px, I'm no longer going to write these three values. Right? Recall that this box, the first one is px, the second one is py, the last one is pz. So they are asking me for px. That means I'm going to give them the value of ml that corresponds to px. When it was just p, I gave them the entire value of p, the possible three values of p, px, py, and pz, which is -1, 0, and +1. But now they are being very specific. They said, what is a ml when px is actually what is involved? So I look here, px is -1. Alright, so my ml for this particular question will be -1. If they have said it to be py, my ml would have been 0. If they have said it to be pz, my ml would have been +1. If they had not put anything here, I would have given them the three values, -1, 0, or +1, because they did not indicate whether it is px, py, or pz. So I'm going to give them the maximum value for all of them. But the very moment they indicate x, I'm no longer going to give them all of them. I'm just going to come here. px corresponds to -1, so therefore, I'll give them the -1 value. So here it comes, my ml becomes -1 for this question. Life and the rest. Once again, if you have any question, the comment section is there for you. Okay, so let's look at option D. Let's look at option D. You have 3dxy. Once again, my n here, the energy level is equals to 3. The azimuthal here is the d. When d is present, the L is going to be equals to 2. Now, we are asking us to give the ml of xy. Now, recall that d has -2, minus 1, 0, plus 1, and plus 2. Let me take our minds back. Now for this minus 2 is the xy, this is the xz, this is the yz, this is the x squared, y squared, and this is the z squared. So they are asking us what would be a ML when I'm considering just xy. Assuming they did not give us, assuming they only said 3D, assuming the question was just 3D, our ML would have been minus 2, minus 1, 0, plus 1, and plus 2. These entire values will be given to them, but the very moment they said xy, I'm now being so specific of the one I'm going to choose. The xy is minus 2, xz is minus 1, so I'll come here and say ml equals to minus 2. That is the answer for this. Alright? So I believe with this particular question now, any question that falls under this, you'll be able to answer them. Now let's move down to number 3 here. Writing designation when quantum numbers are given. Now this is exactly the opposite of what we just did here, right? So let's look at it. Now writing designation when quantum numbers are given, right? Now this is basically what I just did here. So let's look at this question. Example: give the designation for the following quantum number. Give the designation for the following quantum number. A, n equals to 2, n equals to 0, ml equals to 0. B, n equals to 2, n equals to 1. C, n equals to 2, n equals to 1, ml equals to minus 1. D, n equals to 3, n equals to 2, n equals to minus 2. Now, I want to actually replicate, I'm just replicating what we saw, what we got previously, right? Remember I told us that this number 2 and number 3 is actually opposite, writing designation and giving designation, and giving values for quantum numbers with designations are given. So what this is trying to tell us is that, in the first case, they gave us 2s, so we're able to get n to be equals to 2, n to be equals to 0, and n down to be equals to 0. So this time around, they're asking for the reverse. What if they give us these quantum numbers? Would we be able to actually get back those designations? Alright, so that is basically what this is all about. So let's look at this. Let's look at this. Okay, don't worry, I'll hint this part off. N equals to 2, L equals to 0, and L equals to 0. Now, I'll put that here. Recall that for L, we have orbital. Okay, this is 0, this is S, this is 1, this is P, this is 2, this is D, this is 3, this is F. Alright, so in this case now, we'll come down here, we'll put down 2, this is the energy level of the shell. When N equals to 0, now look through this. if n equals to 0, we are asked to give the designation, subshell designation. If n equals to 0, what is the letter that designates 0 is S. And of course, once L equals to 0, ML must be 0. So this particular guy is irrelevant for this. So even if I don't put this, the answer is still going to remain as 2x. Even if I put ML, the answer still remains as 2x. No difference. Alright. So for these quantum numbers, n equals to 2, l equals to 0, and ml equals to 0, the subshell designation for this is 2x. Now, let's look at the B part. For the B part, we have n equals to 2, n equals to 1. Now, this is the energy level I put 2 here. When n equals to 1, it is p orbital. I put p here. So the designation for n equals to 2, n equals to 1 is 2p. So that is the answer for that. Now let's look at this. The C part, we have n equals to 2, n equals to 1, ml equals to minus 1. Alright. Now look at this. I come here and put 2 because this is the energy level, we must always put it first. N equals to 1 is p orbital. I put p. Now what they are telling me, this p is of the one that has minus 1. So you come here and say, if n equals to 1, my NL is always minus 1, 0, and plus 1. And this minus 1 is the px, this 0 is the py, and this is the pz. So they are asking me to give the designation of p when ml is minus 1. So you come here, minus 1 for this is going to be px. Since I already have p here, I'm only going to attach x here. What if they are giving me here to be 0? I would have come here, attach here to the y because ml equals to 0 for l equals to 1 is py. If they are giving me here to be plus 1, I will come here and I will attach z. But since they gave me minus 1, I will come here and I will attach x. That becomes 2px. I hope this is actually self-explanatory. Once again, if you have any question, right, if you don't understand perhaps what we are doing, please in the comment section is all yours. Drop your question. Do not forget to subscribe to our channel if this is your first time of coming to our channel. Alright, thank you very much as you do that. Okay. So that is that for this C. Now let's look at the D. Let's look at the D. N equals to 3, L equals to 2, ML equals to minus 2. Now let me do this now. For N equals to 2, that's the orbital. Our ML is going to be minus 2, minus 1, 0, plus 1, and plus 2. So this is the xy, this is the xz, this is the yz, this is the x squared, y squared, this is the z squared. Okay, now you come here, the energy level 3, you put it down first. N equals to 2 is the orbital. If your N equals to 2, that's the orbital. You put D here. N equals to minus 2. You come here for the orbital. For the orbital, when N equals to 2, N equals to minus 2 is xy. The xy. So I'll come here, I'll put the xy. What if they had said plus 2? I'll just come here. Plus 2 is z squared. I'll have said z squared. But since it was actually minus 2, it becomes the x, y. So that is the answer for this question. Right? Now let's look at the next one. Calculation of maximum number of electrons when quantum numbers are given. Okay. we want to look at the next one here is calculation of number of electrons when quantum numbers are given. Alright, there are so many scenarios whereby you'll be asked to find the number of electrons. The first scenario is when only n is given. If you're asked to find the number of electrons and they give you only n, alright, what you're going to make use of, you're going to use 2n squared, where n is the principal quantum number, where n is the principal quantum number. Alright, example of that, we have example is actually, what is the maximum number of electrons? What is the maximum number of electrons when n is equals to 2? Now remember, n equals to 2 is the L shell, because you have the K, the L, the N, the N. Now this is the first shell, n equals to 1, this is the second shell, this is the third, and this is the fourth shell. Alright, it's very simple here. The answer to this question is 2n squared. Now n is equals to 2, so this becomes 2 into 2 raised to the power of 2. 2 into 2 raised to the power of 2 is 4. 2 times 4 is 8 electrons. So the maximum number of electrons when n is equals to 2 is 8. So of course, if you see a question that they give you guys only the n and you have to find the maximum number of electrons, please just know that the answer here, you're going to use 2n squared. Now let's look at the next scenario. The next scenario, second scenario. Now the second scenario is actually when n and L are given. Now they give you the principal quantum number and they give you the azimuthal. In this case now, the number of electrons is going to depend on the value of L given to us. They give you n and L, the number of electrons is going to depend on the value of L. Now, this is what I mean. Example we have. What is the maximum number of electrons? What is the maximum number of electrons when L is equals to, when L is equals to 1, sorry, when n equals to 3, when n equals to 3 and L equals to 1 plus 4. The answer to this question, we have solution. Now, in this case now, n equals to 0 is s orbital. S orbital can take maximum of 2 electrons. N equals to 1 is p orbital. P can take maximum of 6. N equals to 2 is d orbital. D can take maximum of 10. N equals to 3 is f orbital. F can take maximum of 14 electrons. So first and foremost, we are going to actually combine these together. N equals to 3 and N equals to 1. If you combine them together, this is going to give us 3p. That's going to give us 3p. And p can take maximum of 6 electrons. 6 electrons. So the answer to this question is going to be number of electrons here is going to be 6. Why? Because the electrons is going to be residing on the orbital. So assuming it was s orbital, the maximum number of electrons would have been 2, p is 6, d is 10, f is 14. So what if they have given us n equals to 2 and n equals to 0? First thing first, since they give us only n and L, I'm going to combine this to have 2s. And the maximum number of electrons s can hold is 2. What if I give us n equals to 3 and n equals to 2? Now this is actually 3D. Okay, the maximum number of electrons they can hold is 10. So that is the answer to that. So let's look at the next scenario, scenario 3. Let's stop for this. I'll give us an example. Give the maximum electron when n equals to 3, l equals to 1, and ml equals to 0. Now look at what I'm going to do here. Now this 3 has no business with this because the number of electrons will be determined by ml. Now n equals to 1 is p orbital. L equals 1 is p orbital. So if it becomes, and we have for p orbital, ml is always minus 1, 0, and plus 1. Please remember, assuming this ml was not here. Remember the last scenario we did? If they give us only this and this, the answer would have been 6. That means L equals to 1, that is p orbital. 3p, they are giving us just these 2. The answer would have been, this would have been 3p. The maximum of electron here is 6. But since they have added ml equals to 0, so facing face, L equals to 1 is p orbital. P orbital can further be divided into 3, this and this. So you are asked to find the maximum number of electrons when ml equals to 0. ml equals to 0 stops here. Alright, so what we're going to do first is say maximum number of electrons. So since these p orbitals, they are suborbitals, so 3 of them have the same energy. This type of orbital, we call them degenerate orbitals. P orbital and p orbital, they are degenerate because p has 3 and d has 5. Those 5 energies, they are more like they have the same energy. Those 5 orbitals, they have the same energy for d. The 3 orbitals, they have the same energy for p. So here, electrons will enter singly first. 1, 2, and 3, 4, and 5. I'll stop here because it said ml equals to 0. Alright? So the maximum number of electrons here is 5 plus. What if they had said ml equals to minus 1? This is what would have happened. This is minus 1. I'll come here and I'll circle this. This would be 1, 2, 3. Singly first, 4. Have you seen that? So this would have been 4. As mean they have said ml equals to minus 1. So I'll first of all fill it singly and then I come back and pair. In the pairing, I'll stop where it was indicated here. If they had indicated minus 1, I will stop here when I'm pairing it. If they had indicated 0, I would have stopped here when I'm pairing it. If they had indicated plus 1, I would have stopped here when I'm pairing it. Alright? So in this case now, so let's return back to our normal question, the initial question. Here was 0. Okay? So we say ml is minus 1, 0, and plus 1. So this becomes this. This is where. So this is 1, 2, 3, 4, and 5. So therefore, the maximum number of electrons here is going to be 5 electrons. Now let's look at the case whereby they give us all the four. Please bear with the question here. Do well to ask. Okay, before then, let's look at this next question. Let's look at the second one. Before we move down to 4 quantum numbers. Now what if we had said n equals to 3, l equals to 2, and ml equals to plus 1. they are saying this first, n equals to 2 is the orbital. N equals to 2 is the orbital. Alright? So this is going to be, you now write the magnetic quantum number. So we say ML here is going to be minus 2, minus 1, 0, plus 1, and plus 2. So we have this. Okay. Now, like I said, this really has no business with this, right? So L equals to, I think they have not given us this guy. If it was just these two, so it would have been 3D, and D can take maximum of 10 electrons, right? If it was just these two now, if you combine this is 3D, and D can take maximum of 10 electrons. But since they are asked to add plus 1, so how do we solve for this? Now look up. Now plus 1 is here, you actually circle here. So this is where I'm going to stop when I'm preparing it. So first thing first, these 5 orbitals, they are degenerate. So electron must enter singly first. You cannot just come and put electron here without this source having gotten electron. So this becomes 1, 2, 3, 4, 5, 6, 7, 8, 9. This is where you're going to stop because this is plus 1. The pairing will stop here. So the answer for this becomes 9 electrons. Very simple if you understand the concept. Alright. Alright, so we get this is when N, L, N, L are given, right? The N, the L, ML, and MS are given. Principal, azimuthal, magnetic, and spin. Alright, an example of this becomes, if you actually notice, as they are giving us this, when it was only N, it's the number of electrons depended on the N. When it was L, the number of electrons depended on the L. When it was NL, it depended on this. So when it is NS, it's going to depend on this. So let's see how we're going to do this. So they say, what is the maximum number of electrons when N is equal to, let's say, 3, N equals to 1, Mn equals to minus 1, and Ms, let's put this guy to be 0, Ms equals to minus half. Alright, now look at this. Let's see what we're going to do here. Now first, this is p orbital. So n equals to 1 is p orbital. So it's p orbital. I'll say my NL here is going to be minus 1, 0, and plus 1. Alright. Now this spin being half, the spin being half, alright, simply means that this is going to be the pairing, alright, this is going to be the pairing. So I'm going to stop anywhere we have in this orbital when this guy is half. Okay, let's change this to plus. Let's change it to plus. Let's change it to plus. Right, so let's use ms equals to plus half. Now this one I'm going to do. I'll come here. First of all the electrons that are entering, this is 1, this is 2, this guy is pointing up, this is half. I'll stop here. Yeah? I think this place was minus. I would have entered, come here, because the one that is pointing down is a spin minus, is a minus. I would have stopped here. So this is 5. But since they give us here to be plus, so this is what I'm going to do. Anytime I get to up in this, the place that I have 0, and it points up, I'll stop here, and I'll count these electrons and one that actually came before this particular guy. That is it. The answer for this question is going to be 2. Somehow confusing, but then if you pay attention, you're going to understand this. What if I had changed this place to +1? The spin is still up. Remember, positive spin is the one that is pointing up, and negative is the one that is pointing down. So what I'm going to do is that I'm going to come to NL equals to +1, which is this box, right? The moment I actually get anyone that is pointing up, that is what I'm going to stop. So I'm going to count that electron alongside the one that actually came before that particular one. So this becomes 1, 2, and 3. So if I'm using plus, if I change this to +1, the number of electrons here is going to be 3, because I'm now stopping here. Okay. Now that is that for that particular. We have the last one. Correcting wrong sets of quantum numbers. Now let's say for unpaired electrons, because we're going to do for unpaired electrons and we're going to do for paired electrons. So just look up so you understand. For paired electrons, now what is wrong? Now the question is, what is wrong for the following sets of, what is wrong for the following set of quantum number? N is equals to 3, N equals to 3, Mn equals to +1, and Ms equals to +half. Now let me explain something, class. For paired electron, please, your spin must always be plus, because plus is the one that is pointing up. So if the electron is just one in an orbital, it must point up. You cannot have just a single electron pointing down. So for unpaired electrons, if they give you this place to be negative, this is already wrong. You can only see negative for paired, and you can only have negative when you already have positive, right? So I'm coming back to this. So let's come back to, let's look at this. Your N is 3, L is 3, Mn equals to 1. This. You're asked what is wrong with this, and correct it. Class, remember that N, that's L, starts from 0 and ends at N-1. That simply means that L should never be equals to or greater than N. L should always be less than N. So if N is equals to 3, the maximum number of L can have is going to be 2, because 3 minus 1 is 2. So if you look at this particular place now, N equals to 3, N equals to 3, right? This is actually very wrong, because you cannot have L being equal or greater than N. L must always be less than your N. So this is actually where the problem is, right? So for me to correct this, I'll say this is equals to 3 and this is equals to 2. Or I'll say this is, I will increase the N and see if this guy to be equals to 3. These are the two ways to correct this particular set. Alright, so let me just give us a rundown of correct set of quantum numbers before we come back to this. Let me give us a rundown of this, and we can now solve any question that come across. Class 4. For paired electrons, anytime an electron is involved, that means spin quantum number is involved. Now, for unpaired electron, your ms should always be plus half. For unpaired, your ms should always be plus half. If your ms equals to minus half, it is wrong. Now, for paired electron, your ms should always be plus half, comma, minus half. This plus half is the one that is pointing up, and the minus half is the one that is pointing down. So, if they actually give you something like this, ms for paired electron is plus half and plus half, plus, that is totally wrong. So I've actually corrected that for paired and unpaired electron. Now let's talk about how to correct set of quantum numbers. Now look up. This is N, this is L, and this is ML. L should always be less than N. L should always be less than N. If you see a set of quantum number where the L is equal to the same value of N, or the L happens to be greater than the value of N, that means that set of quantum number is wrong. Your L should always be less than your N. Now, ML value should always lie within minus L to plus L. This is what I mean. For example, if L equals to 1, your ML should actually lie in between minus 1 to plus 1. If your ML is plus 2, is wrong. Plus is outside this range. Now, if your L is equal to 2, your ML should lie within minus 2 to plus 2. That means you can have minus 2, minus 1, 0, plus 1, and then plus 2. Your ML should not lie outside your L. Alright? So, having said that, if I have this set of quantum numbers, if I have N equals to 4, L equals to 3, and L equals to plus 4. Now this set is wrong. Yes, this L is less than N, but then our ML is not lying within the range of this, right? So if I want to correct this, the correct value for L should be from minus 3 to plus 3. Working between this and this guy is outside this range, so this is wrong, right? So I believe with this now, you should be able to solve all your questions pertaining to quantum number. Please do well to hit the subscribe button and encourage us to do more videos. Thank you very much.